Good morning, everyone, or good afternoon, or good evening, or what time is it, wherever you are. It's good to be with everybody today. I wish I were actually with you in person, but I think like everybody, I'm getting used to the idea of being with everybody only virtually. So today I'm broadcasting from my own personal social distancing command center, located in an undisclosed location deep in the heart of Texas. So good to be with you today. Today we'll be talking about understanding transport for 5G mobile services. Today's material is targeted really at transport operators who derive revenue from providing connectivity services and generally between the RAN and the core on behalf of mobile operators. So understanding 5G transport is what we'll be talking about today. Hit the next slide. So maybe before I start, just a little bit about Ribbon ECI. Ribbon ECI is somewhat of a new entity. We are the result of a merger between Ribbon Communications and ECI Telecom, and that merger was just completed about a month ago. We are headquartered in the U.S. We are traded on the NASDAQ stock exchange under the symbol Ribbon. About $900 million in revenue, 140 countries, 4,000 employees, 1,000 patents, and so forth. And we focus on kind of two areas, real-time communications, session border controllers, and voice applications from the Ribbon side, and then from the ECI side of us, packet optical transport. And we bring together kind of an interesting heritage in solving mobility-related problems. On the ECI side of things, we have been a leader in deterministic transport, packet optical transport now for a decade or so. In particular, that led us to very significant, actually 4G mobile backhaul deployments across Asia and across Europe, where we gathered a lot of experience in this subject. As such, we are Ericsson's global partner for transport. They do RAN and core stuff, we do transport things, and we're working together on a number of projects with Ericsson right now around the world. We also, from the Ribbon side of the house, have very large-scale voice over LTE deployments serving up to 300 million subscribers, and very large-scale analytics deployments both in Asia and North America. So that's who Ribbon ECI are, and we have a lot of experience from the transport point of view and from the real-time communications point of view to bring to bear on the subject. So with that, let me go through the agenda for the rest of today's session. I'm going to spend a little bit of time at the beginning talking about how 5G is really taking off. There's some interesting statistics. There's been a lot of hype around 5G, but there's some interesting statistics we'll look at about the ramp up of 5G and how real it is. And then we'll talk about how 5G is just different from 4G in many different ways, and how those differences in 5G are going to force changes on the quote-unquote backhaul network, or force changes on what transport network operators are going to need to deliver to their mobile operator clients. And then finally, we'll spend some time talking about different technologies that are becoming available now to help meet all these new challenges. So in the area of statistics, then, I found this really interesting. 5G is actually the fastest growing new mobile technology that has been in existence, compared to 4G or 3G. There was a projected, very rapid subscriber adoption rate that's shown by this curve here on the set of curves on the upper left. And you can see 5G was projected to have a much steeper adoption rate than 4G or 3G. But actually just recently, Omdia released some research last month indicating the actual number of 5G connections at 17.7 million has actually exceeded the previous projections. So not only do the projections say it's going to ramp faster than 4G, but the truth is the actual connections are exceeding projections. It's a 329% growth over a year ago. So after 1 year of 5G, we have nearly 18 million global connections compared with, this surprised me as well, only about 23,000 connections after the first year of LTE. So 5G, obviously isn't as widespread as 4G is, but it's very real and ramping quickly. The other statistic that I found interesting was just how many commercial 5G launches there have been around the world. Within the first year after the 5G standard became available, we are now up to 70 commercial 5G launches in 40 different countries, and that compares with 12 4G launches in the first year of 4G. So you can see that both in terms of the number of subscribers and in the terms of the number of network operators launching networks and services, 5G is taking off very, very rapidly. And what 5G presentation would be complete without a picture of the magic 5G triangle? Is that right, folks? You've seen this in every presentation. Basically, the point of this to me is just how different 5G is from 4G. It's just not a bigger version of 4G. You have enhanced mobile broadband with its set of requirements. You have ultra-low latency connectivity with its set of requirements, and you have MMTC with yet a third set of requirements. So when you put all those things together and you think about what the transport operator has to do in connecting the RAN to the core on behalf of a mobile operator, there's lots of new things that the transport operator is going to have to deal with. So let's talk maybe specifically from a transport point of view and talk about what some of these things in the 5G magic pyramid actually mean from a transport point of view. It's going to drive changes in many dimensions. 4G obviously it serves one key service. Obviously 4G serves more than one service. It serves voice for sure, but if you think about the types of services that really make a transport network sweat, voice is not a big deal. What really makes the transport network sweat is, people like you and me with our favorite device, and we want to get on Facebook. So that's kind of the key service for 4G. It's served by a shared transport infrastructure. It's focused on people like you and me. It's generally focused on consumers. So from a networking point of view, if I get sort of a best effort experience, I might not like it, but I'm used to it. It's the internet, right? Latency isn't quite so critical. If my favorite Facebook page doesn't load right away, okay, that's not going to break my heart. So the backhaul transport that's existed from that has generally had what I'll call a statistical SLA, which says, hey, on average, you're going to experience this kind of packet loss, packet delay, and so forth. So, it's one basic service. It's got a consumer focus. And when it comes to the transport network, then we're all probably familiar with this, is that the transport is really kind of point to point. You've got a bunch of cell towers at a bunch of remote locations, and they kind of hold them back to a couple of mobile switching facilities in a large metro area. It's basically point to point. You kind of put all that together, and that says that carrier Ethernet is a pretty good backhaul transport technology and a pretty good backhaul transport service offering. It's point to point, statistical SLAs, and so forth. So that's really worked. And in addition, it has a very simple RAN architecture, very monolithic core, so it leads you to put those cores in just a couple of locations. And very importantly, 4G was huge business for transport network operators providing backhaul connectivity service. Some of the things that make 5G a little bit different, again, getting back to that magic triangle, you don't just have one key service anymore that's going to put sweat on the transport network. You're going to have many disparate services, which is going to lead transport operators to need to provide network isolation and slicing capabilities, because you're serving not just consumers, but you're serving consumers and enterprises. In fact, this was an interesting statistic. Telecoms.com just produced a statistic saying that 84% of mobile operators they surveyed are really focused on enterprise applications to get the revenue payback for their 5G investment. And that just sort of makes intuitive sense. I'm not going to pay a lot more as a consumer to look at Facebook more rapidly or something like this. It's really about the enterprise for 5G. So that means, the consumers are there too, so that means you've got a mixture of kind of best effort traffic and really critical priority data type traffic. So the stuff that's low latency and stuff that's kind of latency tolerant, you get stuff that's assured QoS, and kind of or whatever is going to work. So it's a combination of things. And from a transport topology point of view, it's different as well. You're not just homing all this traffic back to a couple mobile switching offices with monolithic cores. Now the core is virtualized in 5G. The core can be distributed. The core can be sliced. The core can be kind of sprinkled throughout your metro network. And on top of that, you can have CU to CU communications going on directly between RAN components. So if you sort of tie in CU communications and the idea that you can split up your core and distribute MEC edge computing functions out there to serve latency sensitive applications, it's not just a simple backhaul point-to-point problem anymore, and it probably leads you to deploy a routed type of solution or include a routing technology as part of the overall backhaul transport offering. And there are other complexities as well. There's multiple RAN architectures. You're all probably familiar with the RU, DU, and CU split. You virtualize the core. You have control plane, user plane separation. The one thing that's the same from 4G to 5G is 5G is going to be big business for transport operators, providing connectivity between RAN and core on behalf of mobile operators. Mobile operators then are going to demand more excellent types of transport service to deal with these challenges, and there's going to be very significant transport operator revenue opportunities that are out there, or stated negatively, there's a chance to lose a lot of revenue if you don't get the transport network right. Okay. So with that kind of intro and lead in, let's take a little bit of a break. And Lance, do you have our first survey today?
Hey Sam, yeah, sure do. So I'm launching that now, and you should see that visible on your screen. Just a quick question: where are you in your thinking about your transport network and services to mobile operators for 5G? As you can see there, the choices are: you haven't considered it yet, starting to study but not yet decided on an architecture. A little typo there, sorry about that. You decided on your architecture but are now looking to select solutions, or the last choice, in deployment now. So that should be there. Just make your selections, and in a moment, we'll get back to the slides. Sam?
Great. Thank you, Lance. Appreciate that. It's interesting to see these poll numbers coming in. It's, this joke is dated, but being from Iowa, I'm tempted to say it's a little like the Iowa caucus, if anybody remembers that. But so just as the poll numbers are coming in, it's kind of interesting. Most of the respondents, very few of them are in deployment now, only a scattered handful. Most folks are started to study their transport network architecture, but not quite decided yet. And 24% is still pretty early for you, and you really haven't deeply considered it yet. And that actually kind of matches with my personal anecdotal experience as I go talk to different service providers about these ideas and kind of get a feeling for where folks are. So it's good. Glad the webinar seems timely. I'm glad you folks are here. There's lots to think about, lots of decisions to make, and hopefully this will be of help to you. So let's trudge onward as I figure out how to operate my keyboard. Thank you for your patience. Okay, so we talked about how 5G is different from 4G and how those differences are going to have tremendous meaning for the transport network. This slide starts to take that into a little bit more detail. And again, I'm really speaking to the transport network operator whose mission in life is to provide connectivity services to connect the RAN of a mobile operator to the core locations of that same mobile operator. You may ask, I'll foreshadow a little bit here. I'm not going to be talking a lot today about front haul. There's lots of interesting technical problems that one could speak about when talking about front haul, but in my experience and my take on the market, front haul, exists within the RAN. And if there's going to be deployments of equipment, it's not really like a lit services offering that a transport operator is going to be, in my opinion, generally successful with. The front haul space is very low latency, it's really very price sensitive and localized. So I see a lot of what's going on in front haul. Mobile operators are trying to obtain dark fiber. That's not really a lit service offering, so they can do the front haul themselves, or maybe some sort of WDM solution they would want from a transport operator. So a lot of the fun technical things to talk about in front haul I'm going to say, are largely the purview of the mobile operator and not the purview of the transport operator. So I'll be focusing on these other things today, if that makes sense. And you can slice it and dice it in different ways, and there's people talk about it differently, and it's all legitimate. I tend to put things into these 6 categories. Kind of the obvious category, transport operator is going to have to deal with is really massive capacity and increased connectivity requirements. So the capacity is going to go up roughly by a factor of 10, and the connectivity needs is not just all point-to-point anymore. You're going to need to connect to a lot of different locations. So that's kind of the first challenge. The second challenge and the third challenge kind of go together. The second challenge has to do with network slicing. One of the big innovations in 5G is the ability to provide what are called network slices, sort of talk more about later, kind of virtual networks that exist on the same physical infrastructure. And the reason you have to do that is to support the wide variety of 5G services that are going to be desired. But you need to do it on a single network with various SLAs and key performance indicators per slice. That is a new problem for the transport space. The transport space can't just ignore what's going on slice-wise in the mobile domain. And related to that in particular is the ability for the transport network to deliver very low latency performance. It's going to be as low as a millisecond for certain applications versus 10 milliseconds today, kind of in the world of 4G. Now, you may be tempted to say, well, you know, if there's a really low latency application out there, I can kind of address that with mobile edge computing. If I've got low latency needs, I'll just sprinkle my edge cloud and kind of everywhere it needs to go. And in theory, that's probably true, but there's economics that are associated with that. As I talk to operators about where they're going to put edge computing, it's far more distributed than it used to be. Instead of just, you know, a handful of locations nationwide, we're maybe talking about a couple of locations in a metro is often the answer I receive. But a couple of locations in a metro is still fairly centralized from a transport point of view if you're trying to deliver low latency. So the transport network is going to need to get involved and implement things that can deliver very low latency transport, guaranteed low latency transport connections. So most of the rest of the presentation will focus kind of on these 3 areas here. There are a few other areas that are very important we won't have time to talk about today. Enhanced synchronization is one of those. With 5G, you can do a lot of neat things at the radio interface in terms of radio heads cooperating with each other to get higher capacity or more stringent location information. And to achieve those things at the radios have to be much more tightly synchronized. And generally that means the transport network is going to need to get involved, maybe even just as a backup or maybe as primary for delivering synchronization to the cell towers. That's going to be actually really important. And then you have things like programmability. If the types of 5G connections are changing rapidly, the transport network may need to be a little bit more dynamic than it has been in the past. So a programmable aspect of the transport network is going to be important, as well as security. So we'll spend the rest of the time today talking about these kind of 3 areas up at the top. So one of the easiest areas to understand logically is just the need for increased 5G capacity and the types of interfaces that are going to be needed in the network. If you divide the network into the transport network, that is, into some tiers, you say, well, there's an access tier, pre-aggregation tier, an aggregation tier, and a core tier, as some of our clients like to think about. The simple number to remember is it's about 10 times the bandwidth that's going to be required for 4G. So you got to think differently, and maybe you'll have to invoke some more optical technology, for example, to help scale the bandwidth, and maybe some other things as well. The other thing to think about is there are a couple new interfaces that are going to be required. 25 gig E, I think, is going to be a very popular interface, especially out towards the access and pre-aggregation parts of the network. And I really wanted to show my favorite internet meme here, but the marketing department wouldn't let me, so I'll just sort of imitate it or describe it to you. You remember the meme where you got the, I think it's the Real Housewives, and they're shouting, and on the other end there's this cat. So the Real Housewives are shouting, I have no more capacity in my network, and the cat just looks at them and says 5G. If that means nothing to you, I humbly apologize. Let's go on. So part of the reason then I guess with in mind the need to deliver greater transport capacity for 5G, many of the operators I'm talking to, and this is backed up by actually some industry statistics, we're starting to actually see an increasing role for OTN technology, layer 1 technology for backhaul by transport operators. There's several reasons for this. One, that the OTN is really good at providing bulk, easy to manage, high capacity. So some folks want to use OTN as kind of an access method, just get some bulk capacity access, then bring that to a packet network that is more in the aggregation or core, let's say, portion of the transport network. And some folks are interested in going to an OTN approach to connect the RAN network with a core network, actually for simplicity reasons. In the days of 4G, transport operator would typically deploy a layer 2 or layer 3 VPN network, and there's many different packet hops throughout that network. And the mobile operator would say, okay, well, today I want a 200 megabit EDC from my RAN to my core. And that was very economical for the mobile operator, but as bandwidth started really increasing, that mobile operator said, okay, I need a higher bitrate EVC, I need a higher bitrate EVC again, and it got to be difficult and time-consuming in some cases for the transport operator to keep up with the increasing demands of the mobile operator. The one good thing about OTN is it very easily anticipates increased capacity requirements. If you're familiar with OTN, it scales in 1.25 gigabit increments, and basically you can just resize the pipe without having to worry about a lot of hops. It's not as bandwidth efficient as a packet-based service, but boy is it simple and boy does it deliver. So I've seen cable companies have an interest in this kind of technology. I've seen telcos have an interest in this kind of technology for those kinds of reasons. And again, I'm often surprised by statistics. So I stumbled across this recently. This was a survey done by the market research firm IHS Markit, and they had a paper called 5G Transport Strategies and Vendor Leadership that came out just a couple of months ago. And they surveyed many different operators, and they said, well, tell me what you think about technology-wise for mid-haul and backhaul. And of course, if you look at the kind of the right three bars here, MPLS has been with us for a long time for 4G backhaul transport, and MPLS is not going to go away. That's going to need to be part of the solution going forward. So you see very strong, 40% of the respondents will consistently see MPLS being required now and into the future. What really caught my eye, though, was the increasing role of OTN. I mean, now, and my experience is borne this out as well, now very few people have used OTN technology as a significant backhaul technology, but that's really started to increase in the last year or two and is projected to continue to increase for, at least according to this survey, maybe half the operators are out there going to invoke some type of OTN component somewhere in their network. And the reason you do this is because OTN can contribute to the large capacity growth. It can also, as I'll show you in a few slides, contribute to the network slicing capability of the transport environment, and it delivers very low latency. So there's lots of reasons why OTN is sort of gaining popularity for 5G transport. Then if you think back to our 5G magic triangle and all the different kinds of wacky things that you're going to want to do with 5G, then you start to get into the latency and the slicing needs of the transport network as well. So this, again, this same survey by IHS Markit that came out just a couple of months ago, when they surveyed network operators and they said, what are your top transport performance challenges? Delivering ultra-low latency in the transport network was the #1 concern. And then related to that is network slicing for Indian performance. So again, it kind of bears out, it makes logical sense if you think about the demands that 5G is going to be placing on networks. So the next few slides, then we'll talk more about the latency and the network slicing aspects of mid-haul and backhaul. So many of you are probably familiar with this, but sort of just in case, a network slice is different than a VPN. A network slice is a logically separate network. You could argue that a VPN is kind of a network slice. I kind of don't like that definition because to me a VPN, at least traditionally, a VPN will create a closed user group where, you know, a group of users can only communicate with that same group of users, and these users can only talk to themselves, kind of represented by the green and black lines here on the chart. But there's not necessarily a separation of underlying network resources. So you get a closed user group, but you don't get a set of underlying resources, but a slice will give you just that. A slice will deliver performance as a separate network. A slice will be managed and operated as a separate network, and a slice is an actual separation of underlying resources. That's a very important point, separation of underlying resources. The slice then, to fully deliver a slice, includes both RAN components, core components, transport network components, as well as cloud and application components. So to really do that right, you've got to hit across on all cylinders, and it's going to involve typically virtual and physical network functions. And network slicing is going to be required to deliver many or most of the 5G use cases. In a lot of the initial 5G deployments, they've basically been, you know, it's kind of a race. You know, I need to grab market share, I need to grab mind share if I'm a mobile operator, so I need to get out there with 5G. Maybe I do some fixed wireless access for residential broadband. Maybe I deliver an EMBB kind of service that's based on 3GPP release 15 or something like that. That's a fine service to offer. It's important to get out there. But those types of services really haven't required network slicing. But if you talk about what's going on in 3GPP release 16, even though it's a little bit delayed due to COVID-19, that's going to be required to deliver many or the most of the 5G use cases. And slicing then in the transport network is going to be essential for 5G. And just since I mentioned COVID-19, I guess I should mention, in case any of you are worried, 5G does not cause COVID. Don't go burn down a cell tower. Speaking to you folks in the UK. Anyway, COVID-19 is not funny. I hope that doesn't offend anybody. I'm trying to make light of a bad situation. So there's many ways, and we talked about slicing in the transport network. There's actually many ways to slice the transport network pie. You can do this different ways. There's no industry standard terminology on this. This is just sort of my language. You could do sort of a network-centric approach to transport slicing, where you say, I'm going to carve out dedicated resources in my transport network by mobile technology generation that I am backhauling. Now I have a section for 4G and a section for 5G. I think that's a valid thing to think about. You may, as a transport operator, want to slice up your network and provide dedicated resources by a mobile operator. If you're building a single network that provides backhaul for example, in the U.S., the 4 major operators, including Dish, you may want to slice your network kind of that way. Another way to think about it, if you look at it kind of the 3GPP point of view, they tend to talk more about service-centric slicing, where you slice, you know, the whole network, the RAN, the core, and the transport by 5G application type, the EMBB, and URLC and MMTC points from the magic triangle. That's one way to slice it. You could also slice it according to end-user vertical. You could say, well, I'm going to be serving an automotive suite of applications here. I'm going to create dedicated resources for the automotive suite. The trick is, if you're in automotive, that's just not one kind of service. There's actually many kinds of services that will go on in automotive-related applications. Certainly, just providing entertainment to a car when it's going down the highway is a different type of application than trying to get a car to avoid another car as 2 cars are going down the highway. So a bunch of services inside an automotive suite, for example, is another way to potentially slice things. And then the finest granularity of slicing is where you slice by application, kind of along the other axis. So I've got cloud gaming and remote surgery or industrial automation or something like that. Then I may want to slice things that way. You can do it in many different ways. None is inherently invalid. It's all a question of what kind of works best for the customer you're trying to serve. So let's look at technology options to provide transport network slicing. And we're about halfway through today's session. If you look at transport network slicing options, they kind of fall into 2 categories. You can think of hard, and again, slicing is resource reservation, resource isolation. So you can think of hard isolation and soft isolation. Hard isolation, you think think TDM, where you have very strict separation between hard pipes, and it's not possible physically at all for traffic congestion in one pipe to impact traffic in an adjacent pipe. And they're very simple. One characteristic of hard pipes or hard isolation is you don't get statistical multiplexing across pipes. It's just the way it is. With soft isolation, again, think VPN, think closed user group. Traffic of one VPN cannot be received by the customers of another VPN. It's very cost effective, get statistical multiplexing out of it, but it is possible, and if your service is very sensitive, it may be likely that if it's not engineered correctly, the network, the congestion in one VPN may actually impact traffic in other VPNs. That would be bad. And as a result, generally speaking, the networks that are built on VPNs, they have an SLA, of course, and some of the SLAs are pretty good, but there is statistical SLA that may or may not, that says on average I'm going to have this kind of packet loss, on average I'm going to have this kind of packet delay. It's not really a guaranteed SLA on a per packet basis, for example. So it may or may not be sufficient for some of these really stringent emerging 5G applications. So if you think of two big categories then of transport network slicing, you bring them together to provide something called hybrid slicing. We believe the hybrid slicing in the transport network is going to provide the best of both worlds, the best of statistical multiplexing and hard isolation. So here's kind of just a very simple picture of what we mean by hybrid slicing. Again, you've got the transport operator here, and his job in life is to provide connectivity services for the mobile operators to connect their RANs to their cores. And you can see in this example, you've defined some hard pipes or hard slices. And maybe it's only on the order of 10-ish, let's say, that order of magnitude. And if you're serving multiple mobile network operators, okay, maybe you have 10 for each mobile operator, that sort of thing. And then inside the hard slice, that's where you can stick layer 2, layer 3 VPNs inside the hard slice. So you still get the statistical multiplexing, you still get the closed user group capability, but you get some isolation on top of it. So one of the things that hybrid slicing gives you then is this very assured traffic isolation capability. So in this very simple example, I've got a 100 gig over wavelength kind of trunk. Inside that 100 gig trunk, I'm showing a couple of hard slices, a big one that's blue and a little one that's yellow. And the big one that's blue, I'm using that for web traffic or EMBB kind of traffic. And if I've got VPNs in here for EMBB, I may want to oversubscribe that. That's okay. And if I get a little bit of congestion, then that's going to manifest as some packet loss, delay, or delay variation. But that loss and so forth is going to be in delay, is going to be limited to only the VPNs within that hard slice. I may have a second hard slice on that same 100 gig wavelength where I stick my mission critical VPNs, and I probably engineer this differently, and I avoid congestion within this hard slice, and any problem that occurs up here has absolutely no impact on the mission critical VPNs. That makes sense? If I delivered soft slicing only and tried to mix mission critical VPNs in with just internet VPNs, let's say, and I experienced some congestion on the enhanced mobile broadband part, maybe I didn't engineer the queues quite right, I could realize some deleterious effects on my mission critical traffic. So that's the big reason, if you had to boil in a nutshell, why we would advocate hybrid slicing to folks. I've seen some talk out there, and you may have seen this too out in the industry, about the virtues of control plane isolation. If you go back one slide, you see really I'm talking about the data plane here. So I see some talk in the industry about the virtues of control plane isolation. I don't say control plane isolation is bad. It creates a logical isolation for topology and path computation and things like that. The VRFs may still vie for common resources, but maybe you can solve that problem. The bottom line is I think control plane isolation by itself, whether it's an embedded control plane or a cloud control plane, however you do it, just providing control plane isolation by itself that's not going to help you with data plane contention problems of queuing and scheduling and who's going to get the next transmission opportunity. So, I would never say control plane isolation is a bad thing. I just don't think it's adequate in and of itself. So if you look at technical choices then for how to implement some of these hard and soft pipes, that's what we'll spend the next few minutes talking about. For hard isolation, you kind of got a couple user plane choices, one of which we talked about earlier, and that's OTN, where you have containers from 1.25 gig to 100 gig or more. To very low latency, you can deploy them point-to-point or ring or mesh type topologies. You get 50 millisecond protection. It's typically implemented on optical equipment, and we're seeing sort of a renaissance in OTN now for mobile transport applications. The other type of hard pipe that can be done is actually found on packet equipment, and you may be less, generally as I talk to customers, they're less familiar with this type of thing, and that's a technology called FlexE that's been extended to something called G.MTN. G.MTU is an ITU standard, and if you like acronyms, it stands for G.Mobile Transport Network, so it's easy to remember. FlexE, you may remember, is something that was brought into being by the OIF, basically to solve, basically to create rate matches between the Ethernet MAC layer and the Ethernet PHY layer and the OTN pipe and the wavelength. It's kind of to solve an efficiency problem in point-to-point DCI connections. GMTN is related. GMTN is basically an extension of, and FlexE is not a network layer. It's just basically a shim that happens here in the Ethernet protocol stack. G.MTN then is an extension of FlexE. It's being done by the ITU, and it's adding OAN capabilities and protection capabilities and becoming a full-blown network layer. And the reason for that is G.Mobile Transport Network is to provide hard pipe capability at a network-wide basis in the transport network. It gives you 5 gigabits. It's not quite as granular as OTN. It's actually less granular. It gives you transport slots on 5 gig multiples that are defined on 100 gig and I think 200 gig trunks now. But it's very low latency. Point-to-point ring or mesh, it gives 50 millisecond protection. So it's got a lot of kind of, it basically is TDM kind of technology put into an Ethernet frame. And it's typically implemented not on optical equipment, it's typically implemented on packet equipment. So it's kind of a different animal and gives you some choices when you think about how to provide hard isolation. We'll talk a little bit more about that, GMTN, in an upcoming slide. And then on the soft isolation side, there's been a lot, soft isolation side, there's been a lot said in the industry on this topic. There's sort of conventional RSVP based VPNs, either at layer 2 or layer 3. They're widely deployed, widely understood. And the problem is, I think, has been well articulated on this. The resource reservation is stateful, so therefore it typically occurs at endpoints only because it's hard to scale that level of state in the center of the network. So therefore the SLAs are kind of statistical in nature because sometimes the center of the network doesn't really have all that level of resource reservation. And I think it's going to be not adequate for some of the 5G services. So the industry is moving toward segment routing, which removes a lot of the state information from the network. And there's a flavor of segment routing that does not have traffic engineering. There's a flavor that does have traffic engineering. And particularly segment routing with traffic engineering, I think is very valuable for transport operators providing backhaul. It's an emerging routing protocol, uses centralized or distributed path computation. I kind of like the centralized path computation method. It's very scalable per hop resource reservation by reducing the network state burden that had come along with RSVPT. So you can guess then at Ribbon ECI, if we prefer hybrid slicing, we would prefer, we would advocate both of these technologies, OTN at layer 1 or FlexE G.MTN, to provide the hard pipe, and then we advocate segment routing with traffic engineering here for the soft pipe that would go inside. And then here's a picture of providing hybrid slicing using G.MTN on basically on one piece of gear. We're providing the hard slice with OTN network layer. I probably need a piece of optical equipment here. I'm just using exclusively packet equipment and I have my individual VPN connections kind of coming in on the client side. They can get mapped to a G.mtn hard slice, and that hard slice can be deployed like a network layer. So if there's a failure here, I get OAM downstream, and there's a protection switch, and that whole hard pipe, therefore, is switched and protected. The benefit of this is I get cut-through capabilities at intermediate nodes. I can bypass the packet processing for all the VPN connections, and I can achieve, remember latency was one of our big issues here, I can achieve a radical reduction in latency at through nodes, kind of on the order of magnitude. Depends exactly what's going on in your network, but it's a pretty significant reduction in latency. And I get all the capabilities that I would expect from a hard slice, the 50 millisecond switching. I don't need to provision fast reroute for individual MPLS tunnels. I get the cut-through switching, and I can do this on a single network element platform that's providing both VPNs and those G.mtn pipes as well. So with that, maybe we'll take a little bit of a break here and do a real quick second survey. Lance, you want to bring that up?
Hey, Sam. Yep, that survey is up. And before I go through that, I just want to mention, I know we're not quite at the end of the webinar, but we are trending that way. So if you've yet to ask your questions, please feel free to do that bottom right of your screen. So poll question that's up now, what transport service characteristics do you think will be most important for your mobile operator customers? So as you can see there, high bandwidth, rapid provisioning / bandwidth growth, isolation of mission-critical services, latency performance, or many of these or all of these. So that's our poll question, and we appreciate your participation. Sam?
Okay. Great, thank you, Lance. Results are coming in. I don't want to name an early winner, because that might affect the voting. We're about 25% of the way through. I appreciate everybody's comments. And by the way, I really appreciate everybody's attendance today. It's I know it's been tough on all of us to not get out and talk to people, so thanks for making the time to be on the webinar today. The results, about half the results are in so far, and I think the all of the above is a very popular answer. So about 2/3 of you are saying all of these things, the latency, the isolation, the rapid provisioning, and the high bandwidth are going to be important going forward. And then amongst those others, the latency is the second highest tally. The latency performance stands out for many folks, head and shoulders even above high bandwidth as being a very important consideration for your transport network. So great, thank you for the good feedback there. So then, just to kind of conclude today's webinar, just have a couple of commercial messages, if you will, from Ribbon ECI. We actually make equipment that is deployed extensively around the world in these types of applications. We have a couple of product lines on the transport side. Our switch router product line is branded as Neptune, and we have a pretty full portfolio of different size equipment, supporting all the different protocols and so forth. And because it's branded as Neptune, we're showing it here under the C. So I hope that doesn't bother anybody. But these platforms, they deliver all those things you need for 5G as a transport operator. They deliver the connectivity. They deliver the network slicing capability. It's low latency. We actually have extensive synchronization capabilities, enhancements that we've made in anticipation of 5G. Security and programmability capabilities as well. And the other part of our product line here, we brand as Apollo. So it's out in the sunshine, and it's our optical transport and switching product family, both full ROADM capabilities as well as full kind of access to core OTN capabilities as well. So we have some very large OTN deployments around the world. These platforms address many of the things we talked about earlier as the key challenges. You can do very high capacity networks. You can use OTN to deliver the hard slicing part of your hybrid slicing solution. Low latency solutions, security capability with OTN encryption that we really didn't talk about today, and again, programmable capabilities. And we bring all of those things under the control of an SDN software suite that we brand as Muse. So Muse is our SDN domain orchestrator in these types of applications where we can perform SDN control for both the Apollo and the Neptune product lines in a highly programmable way. So then in summary, and we'll have a little time for Q&A here afterwards. In summary, many of you are thinking about or just started thinking about what you're going to do to deliver transport services to mobile operators. And that's good that you're thinking about this because 5G is really taking off. Today's carrier Ethernet networks will probably not be adequate for everything you will want to do for 5G transport. And actually, they're becoming a little bit inadequate for 4G today. So a lot of these OTN deployments I mentioned earlier are actually even just for 4G with increased capacity needs. OTN is going to be able to deliver simple, scalable pipes with very guaranteed performance as one interesting technology to consider. And then we spent a lot of time talking about hybrid slicing, and now hybrid slicing, a mix of hard and soft pipes, is going to deliver the best of TDM and statistical multiplexing capabilities to address all these 5G transport challenges. In particular, we talked about FlexEG.MTN and segment routing with transport engineering. And I guess I should mention that there are some folks out there augmenting networks today, even for 4G. OTN was the example earlier. All these solutions that Ribbon ECI offer work quite nicely for 4G and will make you ready for the world of 5G. Great, so thank you for your attention. Lance, you want to move us to Q&A?
Yeah, sure. Thanks, Sam. We do have a lot of questions, as Sam said. Thank you so much for your participation and all the questions coming in. We've answered quite a few, but we had a couple come in, and I'll let Jamie and David chime in as well. The first one, though, that we'll kick it off with is, what's the main drawback to the current carrier Ethernet networks for providing 5G transport?
I think it depends on what kind of network you've deployed. I don't know if there is one main drawback. Certainly the things I'd be concerned about are the quality and the stringency of the SLAs. A lot of carrier Ethernet networks, the SLAs are just fine for the applications that they were designed to meet, including 4G backhaul. But if you get a bunch of latency sensitive stuff out there, and a lot of you were worried about latency in the future, a traditional carrier Ethernet may not be able to meet that need. The second thing you may want to consider is kind of the scale of those networks. Some folks out there have, carrier Ethernet networks which leverage MPLS underneath it, and they were built to a certain scale. And as the scale of 5G comes along, it's difficult to dump all that traffic on that network that just wasn't sized for it. So the short answer is, latency, performance, and size would be the two things I'd be concerned about for some carrier Ethernet networks.
Hey, Sam, we had several questions that came in around who performs the network slicing and who controls how it's done. Can the RAN operator do that? Is it only the transport provider or some combination of the two?
Oh, yeah, that's a really good question. Probably some combination of the two. And there's different models for this. If you look at a lot of drawings and so forth produced by standards bodies, they will often depict an overarching, let's say, controller and orchestrator type of software layer. You might call it a 3GPP orchestrator, if you will. And that single big orchestrator in the sky is touching things in the RAN, is touching things in the core, and then sends instructions to the transport network for what the transport network should do in response. In cases where the transport operator is a different business entity than the mobile operator, that interface between the 3GPP orchestrator and the transport domain controller will need to cross a carrier boundary. I think that's possible. I don't have personal knowledge that there's a lot of that's gone on today, but maybe my knowledge might be limited. But that would be one way to do it. The other way to do it would be to sort of simplify the level of slicing that goes on in the transport network. You sort of simplify it down to just order of magnitude, kind of 10-ish different choices, and then the mobile operator subscribes to one of those 10 choices. So it's a lot less than 10-ish choices. So it's a lot less dynamic, if you will, than if the mobile operator is sort of real-time controlling everything. But it kind of fits I think a lot of business models that exist today in North America where the transport and the mobile operator are different business entities, and it can probably get the job done. So I think technically either can work. It's just a question of where the business is going to settle. If that doesn't make sense, somebody can ask a follow-up.
And thanks, Sam. I think you might have addressed this, but there were some follow-up questions around can you do network slicing if you don't have a 5G core, if they're trying to use it for other applications such as fixed wireless access or things like that?
Oh, yeah, you can do slicing in the transport network. If you really think about it, slicing is a little bit of an overused buzzword, but if you just remember that slicing is the ability to dedicate resources to different parties on the same shared infrastructure, then you can absolutely deliver slicing just in the transport environment, even if the core is not 5G, or if you're doing fixed wireless access or something like this. So all this hybrid slicing capability can actually have applicability beyond 5G. I think 5G is just the most kind of interesting case.
I mean, one thing, David Stokes here, one thing I would add to that is we have talked to a number of transport operators and critical infrastructure operators who are very, very interested in slicing technology and have nothing to do with radio. So, for example, talking to one defense organization, they're very interested in their joint forces communications network being able to put a different slice for the Army, a different slice for the Navy, etc. So if one slice is compromised, it doesn't compromise the other. So I think we'll see slicing used across the transport industry for many different things other than just radio.
Okay. That's a very good point. Thank you, David. So David mentioned the defense application, and there's also ECI, Ribbon ECI provides many solutions for critical infrastructure operators where they'll need some sort of transport environment. And if you think about electrical utilities, one of the big subjects there is what they call OT and IT convergence. And it is nice to be able to offer a slice of the transport network to the operational technology and a different slice, the OT, and a different slice to the IT side. And in that case, there's not necessarily 5G involved either. Thank you, Dave. That's a good point.
Okay, I believe we had one other one here. You talked, maybe you addressed this too, I apologize if you have, but you talked about the reduced latency using hybrid slicing.
Yeah.
Won't the distributed MEC solve all the latency problems?
Yeah, that's a very good question. And I think in theory it can. In theory, I don't think there's a technical reason why one couldn't distribute mobile edge computing kind of wherever you wanted to or wherever it was needed. I think it becomes a business issue. As I did mention this a little bit earlier in the talk, that as I anecdotally, as I talk to operators out there, they are distributing mobile edge computing, but the level of that distribution is a little bit limited right now. So if you maybe have a MEC site or two in a metro location, that's much more distributed than it has been in the past, but is not as distributed as it might be in the future for business and economic reasons. So I think the transport network then, it's not going to get off the hook. It's easy to sort of, if you're a transport person, it's a hard problem, right? So it's sort of easy to say, well, you know, MEC is going to come along and solve this for me, but there's a cost associated with MEC. I don't think the transport network is going to get off the hook.
Okay, very good. Thank you for answering that. So I'll just toss it up one more time. Jamie, David, any other questions that you guys see here? We've got a ton of questions, and unfortunately we won't be able to get to all of them. Rest assured, following the webinar day, we are going to send an email with a link to the replay and slides, and we'll also follow up with your questions if we don't get to them. But David, Jamie, any others to mention here?
Yeah, and Sam, maybe you can summarize a little bit because I've seen it come up a couple different times on how do you select OTN versus G.MTN, and are there advantages one to the other? One of the questions was talking about a very large network deployment where you have a lot of aggregation points in the metro and the core, and you're trying to optimize the bandwidth. Are there trade-offs that they need to look at for that?
Oh yeah, that's a really good question, and unfortunately, it gets a little bit specific. So I'm trying to think of how to answer that in a general way. I think OTN is probably more scalable as a hard pipe technology. You can go bigger with it. There's implementations of OTN that exist in the marketplace. Ribbon ECI have one where you can deploy a lot of OTN switching in a very small package. Most of the Flex-E and G.MTN implementations that I've seen in our implementation is designed as a little bit more aggregation-y and doesn't scale quite as big as the OTN side. If there is a downside to the OTN, you need a separate box. So the packet part's not going to go away. So you're going to need the packet part there anyway. And if your network size-ish is okay, where you can do a hard pipe right out of that packet box, that becomes very efficient. If you need to scale it beyond a certain range, OTN current implementations right now, the OTN scales much more high. But, we'd love to talk with you in more detail about your specific situation, because we've kind of had to deal with that question before.
I've got one other question. Maybe I'll try answering this one, Sam, and you can chime in and I'll read the question. Will the 5G backbone be physically and virtually separate from the 4G backbone, and what impact will that have on the 5G backhaul network? I'll start with that, and then Sam can add in. Basically, the 4G backhaul network's there to provide the backhaul connectivity. It's pretty static. It doesn't have huge constraints in latency. It doesn't have huge constraints in reliability. It doesn't have huge constraints on all those timing issues and the ability to slice. As you start to move into the more advanced 5G services and network sharing type things, you need to really build a network which is able to provide A, that synchronization, but B, also the determinism required, i.e. guaranteed delay and delay variation within limits. So SLAs that have services that have those sort of SLAs, you need a network that can do that. So ultimately that 5G network needs to be a lot more deterministic with a new timing network put in place. You can either do that by trying to evolve your existing 4G connectivity, which will be difficult, or put a 5G backhaul network as an overlay using the components of the 4G that's in there. But I mean, Sam will go into that in more detail. Then just picking up one other question that's tied to that slightly, will that path across the network be computed manually? Absolutely not. It'll start to get too complicated, and there's elements called path computation elements that do that compute. And as Sam said, this is a big ecosystem, and you have to interwork in multi-vendor networks to do this compute. And we've operated with and in many test beds where we've proven interoperability with other people's PCEs to show that we can do this automatic provisioning of deterministic connectivity across that network. Sam, got anything to add to that?
No, I don't think so. And I think it looks like we're coming to the end of time. So this has been great. Thank you again for attending, everyone. And most of you probably know how to reach me. I'm on LinkedIn. If you got follow-up questions, you can send them to me or Lance as well, I guess.
Yeah, thanks, Sam, and thanks, David and Jamie, for attending, and obviously all of you for attending. I think we might have one or two more slides if you just want to advance quickly there, Sam. I did want to mention, again, replay is coming later this afternoon. You'll have a link to the replay. We'll also have the slides for you. We do have a few more webinars coming up in the next 2 weeks. Optical and packet networking solutions for regional carriers. You can click that button right there to register for that. Cloud and edge solutions for service providers as well on the 26th. And then we have a few others where we don't have the links ready yet, but just take note that additional webinars are coming down the pipe. And by the way, all these are on YouTube after we have the replays up. So please subscribe to Ribbon Communications on our YouTube channel, and you can never be sure to miss any of our additional replays. And then, as Sam mentioned, there's your contact info. Reach out, send us an email. We will be answering these questions, following up in the coming days. But if you don't hear from us in a timely manner, or if you just have additional questions, here's all the experts we spoke about today. So please reach out, and we'd love to hear from you. So again, thanks everyone for your time today. We're going to go ahead and close things out. A brief survey will pop up. Be sure to participate in that, and we will talk to you all next time. Thanks so much.